first off, I'll be uh, talking about this open public alert timeline for gravitational wave alerts. This was basically the timeline for O3. So, the time to send out an automated alert is in this first square on the top with all this blue stuff. So essentially there's all the work that's needed to first send the original detection, and then there's some processing to group up all these interesting events into a preferred physical event, some stuff having to do with source classification and sky localization, and then some automated vetting. But for this talk, I'll be focusing everything up until the original detection for detector characterization. So this is a simplified low latency data flow for O3. There's a lot of things missing, but I want to highlight just a few different aspects and some delineations for basically the latency incurred at various stages up until we get into the gravitational wave searches and the detections themselves. So first off, we have the detector. It creates a lot of data. The strain and auxiliary channel data is available on order 1 second. Then there's basically several parallel paths going down, doing various processing. So I'll focus on the bottom branch first. So the detector itself creates something, a channel in which you can interpret as the gravitational wave strain already. So, but there's this calibration pipeline that effectively does a lot of work to reduce the calibration uncertainty, does things like apply time-dependent correction factors, things like doing linear noise subtraction, removing some of the calibration lines so that the gravitational wave searches have this strain data that is very sensitive to use for the searches. And then finally, the searches process the strain data, and we can get detections out. Now on the upper hand branch over here, this is what I'll be talking about today. So effectively, you can kind of think about this as a parallel path doing detector characterization prior to the searches, so that the searches have this detector data quality information that they can use to inform the searches as to which times are glitchy or not. So first off, I'll focus on the detector noise itself. So there are various noise types in the detector. I like to classify this into 3 different regions. So on the left, you see this power spectral density estimate. So stationary noise can be effectively fully characterized by a PSD. But there are things that kind of just like pop in and out of existence. We call them non-Gaussian noise transients, glitches. There are various names for it. On the top right-hand side, we have a picture of a blip. We've seen this in some of the other talks. They are very well localized in time and frequency. These may last small fraction of a second, sometimes a few seconds. And then what I like to call on the bottom right, more medium duration non-stationary noise. So this is, I believe, from elevated ground motion, but you can see that it's less well localized in time. It lasts tens of seconds to minutes and can really plague the detector sensitivity and make it hard to search for, for example, binary neutron star events. So the ways you kind of deal with these different noise types can be different. Now, noise sources. So the detector is a very complex instrument. On the left here, we have the optical configuration for this. So there are many ways in which noise can couple into the detector. For example, we saw some examples of scattering earlier, photodiode saturations, many other places where it can come from the detector itself. But in addition to that, we have sources of environmental noise that kind of pop in. They could be site dependent. For example, logging plagued the uh, Livingston detector in the second half of '03. We see sometimes very high winds that can sometimes play the detector. On the bottom right is someplace near Hanford. There are tumbleweeds that sometimes can cause you know, elevated noise. So yeah, we have for this reason, we have many different auxiliary sensors in addition to the gravitational wave strain. Um, a lot of these, for example, in Gabriele's talk, they're used to control the instrument itself, for example, for the lock acquisition. But in addition, we have all these auxiliary sensors, things that monitor the physical environment, things like wind sensors, microphones, seismometers, etc. So it's a lot of data. Uh, Overall, the entirety for, I believe, I don't know, '03 around now, we record about 250,000 auxiliary channels. Um, about 5,000 of those are fast channels, and by that I mean the sampling rate is at or above 256 hertz. The rest are very slow channels, so they're recorded at 16 hertz. Now, if you look at the data rate, it's about 50 megabytes per second for the uncompressed data. Um, that may seem like a small or big number to you, depending, but for example, if I wanted to stream the uncompressed data to my house, my internet connection is not fast enough to actually deal with that. And the data storage per site is about 1-2 petabytes per year. So the last thing I wanted to cover in the detector noise aspect is noise mitigation techniques and in order of my personal preference on how to deal with this noise. So for example, first off, we have noise source removal. Uh, so a very good example of this was the RC tracking we saw in Gabby's talk about scattering. You know, we understand the physical mechanism in which noise couples to the detector. We have some way of removing it so that it never enters the strain data. Best case scenario. Um, After that, we could deal with subtracting the noise coherently. So for example, uh, Gabriela's talk was talking about removing these sources of noise from, example, let's see, signal recycling cavity noise, or for example, some of these 60 hertz sidebands. We also saw some examples of, I believe, Alejandro's talk talking about, doing this denoising scheme and being able to remove, for example, glitches, and that would be another way of subtracting this from the strain data. If we can't do that, it's that's also very tough, and there are some examples in production, but it's for glitches, it's still very much a work in progress. After that, what we can do is just say, hey, we found some noise. Um, there's some noise, there's some noise, and then the searches are left to deal with, for example, how do you deal with this in an optimal way within the searches? It could be in a search dependent way. Um, and then finally, you know, maybe we have no way of dealing with some of these at all, and it's left to the searches to kind of mitigate this noise or deal with it somehow. Um, but you know, some of these are what I would like to call complementary to each other. So for example, the noise identification schemes, just because they're lower down on the list for me, are very much useful for being able to inform detector characterization experts to be able to do things like removing the source of noise and understanding the physical couplings. So all these working in tandem are very helpful to be able to find more gravitational wave detections. For the rest of this talk, I'll be talking today about noise identification. Uh, since, yeah. All right, so now I'll focus on the top half of this branch, and I've split this up into kind of two parts. So effectively, the two parts are first, identify sources of non-Gaussian noise or non-stationary noise in single auxiliary channels and the strain data. And then from there, we can take that information and try to find statistical correlations between these different auxiliary channels, and then say whether or not there is, you know, non-stationary noise in the strain data. So I'll first focus on the first part, which a tool that we created called the Snacks Toolkit. I like bad acronyms. I think astronomy is pretty good at developing some of these acronyms, but whatever. So this is stands for the Stream-Based Noise Acquisition and Extraction Toolkit. So the basic goal here is extracting non-stationary noise features in low latency. So if you're familiar with compact binary searches, the way to think about this is basically a match filter pipeline using sine Gaussian waveforms. And then the output here is time series data containing some of these noise features. So on the bottom right, you have some of these features here. The first two corresponding to the SNR and phase from the match filter output, the time of the match, and then the central frequency and quality factor of the sine Gaussian, basically fully describing the sine Gaussian waveform that I use to match filter with. And then we can take all that information for multiple auxiliary channels and then combine it into a feature vector. So this is a little bit more of a detailed workflow. So from left to right, we read in these auxiliary channel time series. We do some signal conditioning by high passing and then widening the data. We do an extra step here after this to kind of split this up into multiple frequency bands for computational efficiency. You can imagine, you don't want to use the full sample time series, if you're trying to filter against a waveform that is only like, 30, 40 hertz. So it's a computational here. Then we finally match filter all the waveforms for a given frequency band, record these match, and then generate buffers that are sent, to the other tools. So before I go a little bit further, I just wanted to give an aside about latency. So, when you only have a few seconds of latency, before you need this information to pass off in the searches, trying to account for that in the pipeline is very important. For example, if you wanted to create a spectrogram and stream this, then you have to take into account whether or not there's any information you may need from the future. For example, to create the spectrogram in low latency and stream it, you need 2 seconds in the future, so that automatically incurs 2 seconds of latency. So now I'll kind of look through the same workflow, but then talk about the latency budget and see if we kind of meet our demands here for making sure that it's available by the time the searches can read it. So going back a little bit, so we see that by the time calibration is done, it's on order 5 seconds. That's roughly how much time, how much latency we can incur before, it becomes less and less useful to incorporate this data quality information. So looking here, first off, we get this time series in 1 second's buffers. So the oldest timestamp in that buffer could be up to 1 second old. So it's 1 second there. Signal conditioning, high passing the data, we use an FIR filter that has a 1 second latency attached to it. Now, widening the data itself, you would think that, maybe creating a widener, it would incur the cost of half the FFT length used to do this, but there's always a trade-off when doing creating an FIR filter, which is, you can have an acausal filter and grab all the properties you need, and it's, almost perfect or whatever, but you can trade off latency for, effects or negative effects that could impact the result. So for example, here, what we traded off here was a zero latency widener, but that has its phase response that isn't perfect. So for example, it accumulates a phase offset, which is kind of dependent on the PST. So for example, this wouldn't be suitable for a compact binary search, but for us, we're willing to accept this. Turns out that downsampling the data with the sync interpolation scheme also incurs a second. Match filtering the waveforms, sine Gaussians are symmetric with respect to the center. There's an acausal component. There's a little trick that we use, which is to taper off some of these long sine Gaussians. You can imagine the high Q, low frequency regime that these waveforms are very, very long. So we trade off some SNR here for making sure that the acausal component is very short, and then the rest doesn't really accumulate latency. So total, we have 4 seconds, so we're good. This is kind of a lower bound. There are things like, you can imagine that each of these aren't instant, but take a little bit of time. Also, there's like data distribution costs from getting the time series in, to the node that you're processing the data, but this is, roughly off by, in practice, about half a second. All right, so now that we extracted some of these non-stationary features from these single channels, we can then start to make statistical correlations and start to identify noise in the strain channel. All right, so this is the tool that we created for this was called IDQ. So basically the goal here is to search for statistical correlations between the auxiliary's detector, or the detector's auxiliary state and the strain data H of t. And then the output is basically a probability that there is a glitch in H of t as a function of time. So then the searches can then use this information and then either use it to veto times, or for example, even incorporate it into their likelihood ratio statistics, or as part of their modeling itself. So we pose this as a two-class classification problem in which we have glitches, or we have not glitches or cleans by the capital C here. This is posterior probability here, and then we kind of rewrite this through Bayes' theorem in terms of the priors P of G and P of C, and then the likelihoods P of A given G and P of A given C, where A vector is the feature vectors that we're feeding into this. And then on the bottom here is basically an example time series stripped away from its actual GPS time. So, you can't tell which time this actually occurs, but it's kind of an example of the type of data that gets produced. Okay, so this is roughly the workflow for IDQ. Both, you can kind of think about this both offline and online. So we have interferometer data, which has auxiliary channels. We have some sort of feature extractor. It could be from the tool I showed earlier. It could be from other things. Produces features. And now this little, what I like to call, this cloud here with segments. So you can imagine that we may not want to analyze all times, but let's say just the times in which the detector is locked, or just science times. And so that filters our initial data set. So then on the top right here, we have, first we train our model using the features and the segments. we create a model as its output. And then what we can do is create an evaluated data set using that model and the input features, something called quivers here. Well, kind of jargony, but it's effectively an evaluated data set. Then finally, using this model and this evaluated data set, we can then create from the model's output, create our, how do I like to say it? These glitch and clean distributions, which then we can use to create probabilistic statements, things like doing a likelihood ratio test. And then finally, we can combine all this information together and then create time series. And then fed downstream, searches can use it. We can do it for candidate follow-up. All right, so this is kind of another way of looking at the same data. So we have input features that are n-dimensional. We have this superflight classifier that makes a model that maps these feature vectors into a scalar rank from 0 to 1. Some of these, well, I'll just leave it at that. And then what we can do with that information is create these maps, effectively these glitch and clean likelihoods. Using all our samples, we can create KDEs to model those distributions. And then from that information, we can generate predictions. So given our glitch and clean likelihoods, we can take the ratio to do our likelihood ratio. And then we can also create a P of glitch itself, which also takes in a prior. So some of the features of this is, not to be confused with feature vectors, is that in the online case, we periodically retrain the model to kind of deal with the fact that the detector is, non-stationarity. There drifts in terms of the PSD. They're glitch classes that pop in and out of existence, so we want to capture that as fast as possible. Because of this, we may train new models. We want to figure out, for a given time series, what model was used to train this time series. And so there is some aspect of provenance tracking. And then finally, I didn't specify exactly which features are here. They're relatively back-end agnostic. So for example, the Synapse tool I talked about earlier, some of you may be familiar with Omicron, but in practice, it could really be anything as long as they're discrete triggers that are used to feed into this analysis. And finally, it kind of supports a variety of supervised classifiers. First off, it was designed for these statistical veto algorithms for this ordered veto list, or some may know HVeto or things like that. And then some of the classical machine learning classifiers via scikit-learn, gradient boosting, deep learning. So I think someone mentioned before IDQ, whether that's machine learning, and I would say it depends. If you use a statistical veto algorithm, I think most people wouldn't consider that to be machine learning, but maybe. But the rest are definitely. So yeah, so it's pretty flexible in that respect. I think most people wouldn't have heard about these statistical veto algorithms. So effectively, this is kind of this domain-specific algorithm used to identify statistical correlations between a target channel, in this case, the strain, and all these different auxiliary channels. So the basic idea here is you apply a veto configuration with a given threshold window. So you imagine that there are these glitches, and if you see this green time series DARM error, it's like a surrogate for h of t. You imagine that there are glitches here. You can create a veto configuration, which you can specify the threshold, and then a window to create a veto with, which has some time that gets removed from the analysis. And then you can ask the question, what fraction of glitches are removed from the strain channel given that you applied this veto configuration to a given auxiliary channel. And then you can also compute what fraction of dead time is introduced by applying this veto configuration, or another way of putting at it is um, what fraction of analyzable time gets removed by applying this. And then you can create this metric called the veto efficiency, and then you can repeat this for all these different threshold window combinations for auxiliary channels. And then there's some down selection happening to remove from this full list to just a smaller list of what statistically significant veto configurations. So that's kind of the input that we use. This algorithm's kind of used for production currently for, because it's worked pretty well for us, and it's interpretable. You can kind of see, if you investigate for a given time, you can kind of see which auxiliary channels were active and applied, uh, um, were used to identify the glitch at a given time. So finally here I have a few different examples. So this is GW170817. There was a glitch 1 second before. I believe it was a ADC overflow and electronics overflow. On the left top right-hand side, you see the glitch 1 second before, this in spiral track in the dotted line, and then on the bottom you see a auxiliary channel that witnesses this glitch pretty well. And then on the right here, you see that same time frequency spectrogram. So one other data product that we produced in low latency are these vetoes contained in this thing called the DQ vector. It's essentially handcrafted vetoes, which are shown to be active very often when there are, certain types of glitches or like photodiode saturations or what have you. And they're known, the physical coupling is pretty well known. And so we're comfortable kind of setting that ahead of time and then, identifying this. So this is one particular example where it didn't identify this glitch. And then on the bottom here is effectively what I like to call these feature importance plots that come from OVL. So for example, you have time on the x-axis, you have these veto configurations on the y-axis, and then it's color-coded by rank, which is basically the classifier's output. So for example, higher rank means more likely that it is a glitch. So here we see 4 different auxiliary channels that were active during this time with some information about, how big the vetoing window was. So this, for example, could be used to inform other Descartes experts and finding physical couplings and, sources of noise in the detector. Here's the second example from IDQ. This is a radio frequency whistle, has this funny looking V shape. If you listen to it, it kind of sounds like a whistle, hence the name. These are also witnessed very well by auxiliary channels. Here's one such example from this, from the alignment, sensing, and control subsystem, basically that controls the interferometer arms. In this case, there is no such, handcrafted monitors that picked this up, but Veto or OVL within IDQ picked it up quite well with many of these other auxiliary channels. Some of these may look repeated, I believe, but they're effectively different veto configurations for the same channel, if that makes sense. So this tool works pretty well for identifying any sort of glitches that have auxiliary channel witnesses. And yeah, it's been running since the third observing run pretty well. So the final slide I have here is kind of a wish list for online data quality. Um, so what I'd love to see here is kind of more tools in this whole automated noise identification and mitigation section. Basically, how can we feed in more information for the searches so that they're better informed um, and we can reduce things like alert retractions. So, for example, um, medium duration noise that I talked about earlier, IDQ is pretty good at identifying very short duration transients. It's not so much that it can identify them, but that it's less sensitive, to these because one of the things is that it takes into account only a very small period of time. So if you have glitches that are active, for tens of seconds or minutes, it by default it's a little less sensitive to that. Um, the other main thing, which is kind of a tricky problem, is how to identify noise transients that only appear in the gravitational wave strain. Um, right. So canonical example for this is blips. Blips only show up in HT. They plague high mass regions of the BPH space. There are ways of identifying these, but one of the big problems is that how do you identify this in a way that is safe and doesn't accidentally veto actual gravitational wave events? So there's, I feel like there's a lot of work to be done here, but would potentially pay off very well. Finally, I'd like to see, more more of a push in noise subtraction for short duration transients. So, Gabriele showed this nice stuff about removing quasi-stationary noise from which, um, using this noise, non-stationary noise subtraction. It is very good in that aspect. And, one thing that I haven't seen in production yet is being able to subtract out uh, glitches, which would be absolutely great because it never shows up, or it gets removed from the strain, and then the um, searches, then you have a more sensitive search. Um, some other things that are very much well in the works now, but is still very much an open problem, is incorporating of non-binary data quality information into online searches. So up until now, a lot of what we worked on in the searches are applying vetoes and doing things like auto gating within the searches, but being able to incorporate probabilistic information is very much an open problem. Some of that may be search specific, but there hasn't been too much work, at least I don't think, in this sort of realm. And then finally, lock loss prediction would be absolutely awesome. We saw some really cool work by Marco to, you know, with this whole fractal stuff, to be able to potentially predict lock losses, and I'd be very excited in seeing that, you know, move forward. Um, right, so I'll leave it as here. Thanks very much. Happy to take any questions.